Hi, everybody. Let's get started. Oh, I'm supposed to turn this on. Nope, I'm just noisy. So just so you know, there is a midterm, not next week, not the week after, but the week after that. It's going to go through the lecture on the Friday before that week. So not the Monday before the Wednesday midterm. It's going to be going through the Friday lecture, however far that gets. It's, half page to page answers. There's 100 points on it. 10 and 15 point questions. None of them are how many fingers am I holding up behind my back, anything like that. It's all going to be done as timed, but you have a lot of time, like 3 hours. No book take home that you do on grade scope, and the reason for that is that we used to do like paper tests in a big auditorium, and the problem is we have to disassemble them and reassemble them because every section gets a different test, right? There's a lot of overlap, but it gets a different test, and that is prone to error, right? Because then it goes out to graders, and then they have to come back, and a single missing page is then, a catastrophe. So this is just a much more prudent way to do things. Now, where I ended last time was, I think here, dominant uncertainties in climate change prediction. And on the physical side, it's this cloud albedo feedback, which isn't that big, but is still the dominant, uncertainty on the physical side. And that's because clouds are controlled by physical properties that are physical interactions that are highly heterogeneous and microscopic at scale. And so although it's known what the physics is, it's impossible to implement it at the scale one would need to simulate the globe in a computer program. And so you can't actually simulate the physical processes. You have to have some fancy pants way of scaling what will happen at the grid scale. And there's still a lot of uncertainty about what those are. It's one area where if you're a theoretical physicist, you could really contribute to the climate change literature by coming up with a closed form scaling method. The second big uncertainty, and this is really the big one. I mean, at this point, this is the big one. Future anthropogenic emissions. I mean, it kind of goes without saying. But if the globe decides to go to net zero, there's a lot less global warming than if we just abandoned it and burn it all. This is the AR5's set of concentration scenarios and the emissions per annum that they imply, and in different models and in different ensembles, and you can see how uncertain that is. My guess is that if we fail, we'll do something like that, and if we succeed, we'll do something like that. So I think blue is likely to be success, and failure is likely to be something like brown at this point, but I'm not sure about that at all. And the third biggie are what you should think of as carbon cycle feedbacks. The most important one is represented by this refrigerator door full of vegetable matter. If you open the door to your refrigerator and leave it open, your vegetables will return to the atmosphere at an accelerated rate, okay? And even if you're putting vegetables in at the same rate that you used to, you'll have less biomass in your fridge than before because it's going out into the atmosphere at an accelerated rate. When it decomposes, it goes to the atmosphere, right? That's what happens. Bacteria and fungi eat it and return the carbon compounds, turn it into CO2, and put it into the atmosphere. So in the Arctic, as we warm the planet, the Arctic warms disproportionately. High latitudes warm disproportionately. And there are centuries worth of undecomposed organic matter resting in those high latitude soils that are maintained there because of slow decomposition from the cold temperatures. And so when we heat that up, that CO2 starts to come out. There's strong evidence that it's already coming out. And it goes into the atmosphere, and that causes the temperature to get higher, which causes the warming in the Arctic to be higher, which causes it to go faster into the into the atmosphere, and it's a positive feedback. As we'll see, currently there's a second effect, and that is that plants eat CO2 for a living and turn it into plant. And that effect is a negative feedback, and it's currently globally larger than the positive feedback in the Arctic. But it won't stay that way, as we'll find out later today. And so when this carbon cycle feedback in the high latitudes kicks off is one of the big uncertainties. Okay, so that's what I just said. And next lecture is this lecture, so we'll discuss it soon. I want to close this one out by saying that the evidence about global warming is multidimensional at this point. There are many, many different kinds of evidence acquired now over more than a half century by many thousands of people. And at the beginning, one of the things that's worth understanding is that in science, you don't get ahead by showing that everyone was right all along. You get ahead by showing that everyone is wrong, okay? You get ahead by showing that there's some old paradigm that isn't complete, and you have a new one that is. And that means that if I could actually show that the global warming story was fundamentally flawed because of some unknown feedback that nobody ever heard of, I would become the most famous, probably scientist, period, in the world. And so, you know, winning a Nobel Prize is not just winning the Nobel Prize or something. You actually get several $1 million when you win the Nobel Prize, right? So there's this gigantic incentive to tear it all down. And every year, there's more than 1,000 newly minted PhDs, some of them highly ambitious. And what do? They sit around and they think about, what can I tear down? What's wrong? What can I tear down and then put myself in place of? And right now, all of the contrarians that are left are in their 80s and 90s. So just think about that age distribution and what it implies, okay? I've tried, right? I've funded all kinds of work and been engaged in it myself trying to falsify basic tenets of global warming. And everybody there are some that just go along, to be sure, but they don't get anywhere, right? And so this is the point, is that the idea that people go along with a bandwagon to get grant money is just BS of the highest degree. The incentives are to show everyone's wrong. And you think I wouldn't get grant money from industry if I showed that it was all a mistake, okay? So think about that. So I'm dividing the evidence into 3 hoppers. This is one hopper. This is the Vostok ice core. I like to put this here because you can actually go touch the Vostok ice core in Geel Hall if they let you in there, okay? Michael Bender is a guy who's done so many of these measurements over the years. He's emeritus now. And what the Vostok ice core is a continuous ice record that goes back to 800,000 years in Antarctica, and a place in the center of Antarctica near the Russian base of Vostok. And there are bubbles trapped in the ice that are old, right, that went in there when the ice froze. And you can look at chemical fingerprints of the temperature in those bubbles. And you can look at the CO2 concentration in those bubbles. And they go like this, back through time. And that means that every time the CO2 goes up, the temperature goes up. And every time the CO2 goes down, the temperature goes down. And this has been happening for a long, long time. Recently, we funded a bunch of work. My grant funded a bunch of work to find even older ice than this. And we subsequently came up with some multi-million-year-old ice. And it's also consistent with this record. And so just on the face of it, you should see that there's some link between temperature and CO2, and it goes back in time as far as we have really a continuous record. And then if you look at less secure evidence that is geological in nature, back much deeper in time, these are millions of years, not hundreds of thousands of years, every time it gets cool, every time there is a glaciation, so these are glacial episodes over the last 400 million years. Every time it gets cold, the amount of CO2 in the atmosphere is low. And every time it's hot, the amount of CO2 in the atmosphere is high. And so this relationship between CO2 and temperature just goes way back in time, right? Indeed, one of the things that is worth knowing is that the CO2 in the atmosphere during the age of the dinosaurs was much higher than it is now, as high as it would be if we burned all the oil, gas, and coal. And indeed, there was no ice anywhere. There were, you could find alligators at the tip of Greenland, 77 degrees north latitude at that time. Okay. So a common argument by those who claim that the scientific consensus is suspect is that the climate has always changed in the past. I'm sure all of you heard this. The climate is always changing. You can't attribute it to people. Given the geologic evidence you've just seen, should the fact that the climate has repeatedly changed in the past make you more concerned about fossil emissions or less concerned? And so just do a clicker thing to get that out of the way. We may do another one later. More or less. Huh? Did something wrong? Like, okay, so finish up. There's really no right answer here. I mean, I have something in mind, but so just click a button. Okay, I think that's close. Yeah, there we go. All right, click results. Yeah, so you say more concerned. That's the answer, obviously, I was looking for, and the reason is that in the past, whenever the CO2 has gone up, the temperature's gone up, and whenever the CO2 has gone down, the temperature goes down. We know now that we're putting CO2 into the atmosphere, all right? We can see the CO2 in the atmosphere has the same isotopic fingerprint as fossil fuels. So we know it's us, right? We know the extra is us. So should we be surprised if what always has happened in the past when the climate changes now changes from putting CO2 in the atmosphere? And the answer is no. It should reinforce your view. We also understand the mechanism, right? It's the greenhouse effect and the positive feedbacks that cause the link between temperature and CO2. But the point is, yeah, the climate has always changed in the past because of geologic changes that cause CO2 in the atmosphere to fluctuate. Now we're causing CO2 in the atmosphere to go up, and so we should be surprised that it does what it's always done in the past, except we're now not ready for it, right? We're aligned as a species to a climate that's been stable since we developed civilization and an industrial society, since we emerged from the Paleolithic. The second line of evidence is that obviously now there are records from the historic period, all right? Every year it's warmer than the last. That's not quite true, but certainly every decade is warmer than the last. CO2, methane, nitrous oxide, all going up. They're just a gigantic number of observations consistent with a changing climate, and very few that aren't. This is just a, oops, sorry. That's just a global temperature record. This one from a group called Berkeley Earth. I like this group because they were funded by the Koch brothers, who were prominent contrarian funders, big fossil energy fortune in Texas. And there's a physicist who's a contrarian kind of guy who said, yeah, I'm sure that this is all a sham. And so started his own reanalysis of all of the thermometer and other temperature records around the world himself. Set up a big group. There was a big fanfare on contrarian communication outlets. And by analyzing the data, he discovered that, lo and behold, it really is getting hotter, you know. And so now he's one of the strongest proponents of global warming. The level of ego is such that he says, well, we didn't know that before, but now that I've done it, we do, okay? But nonetheless, you know, you take what you can get. And this is a person who follows evidence. That's the important thing. An honest skeptic who follows evidence. Finally, there are, these are more records from the historic period. sea ice extent, sea level changes. We'll talk about a lot more of those later. There's just a highly multidimensional thing. Also, scientists check each other all the time. So it turns out you'd like to know, are Antarctica and Greenland deglaciating? It turns out that's really hard to do, right? You can go and you can like stick stakes in the ground and drill holes and try to figure out how much ice there is. But you got to do it all over Antarctica and Greenland. And it's really hard to work there. You get killed and get eaten by polar bears or froze to death, stuff like that. And so people want to do it, but it's really hard because as the temperature goes up, warm air holds more water vapor than cold air. And so unless it's really, really, really cold, you get more snow, like on the edges of these continents or big islands, and less snow in the middle. And it's the balance between the growth and the shrinking of these glaciers that determines the ice mass loss. So it's a small difference between two big numbers. So people did it anyway and came up with a view that we had accelerating ice loss, but nobody was satisfied. And so we launched the first of, well, a pair actually, of several satellites. This is the first pair. And these are satellites that actually measure, they were together and they're watching each other, and they're actually measuring the mass at the surface. And when the mass at the surface underneath them changes, their orbit changes slightly. And so the orbits of these two things relative to one another as they pass over a mass change in some way. And you can measure very precisely, then, a change in mass on the surface. And so these are data from this so-called GRACE mission. And what it shows is that there's been accelerating ice loss in both Antarctica and Greenland, just as the first measurements confirmed. But we weren't satisfied with that. And so scientists continued to build other kinds of satellites. This is a fancy pants LIDAR, laser altimeter, that last year released an extremely detailed map of the ice loss and gain in Antarctica and confirmed what the GRACE mission has shown. That's the third data set, independent now. And finally, a guy who died last year at 102, who was a famous oceanographer, in his 90s was sitting around thinking about this, and he thought, you know, the Earth with ice loose being lost near the poles is like a spinning ice skater. And it's like a spinning ice skater because it's spinning. And because when the ice is lost near the poles, right near the axis of rotation, it spreads out over the whole globe, and most of it is in the big fat parts of the ocean at the equator, right? Far from the axis of rotation. So it's like the ice skater spinning and putting her arms out. What happens? Her rotation slows, right? You can see it in your mind's eye. So he said, if that's true, we have these fantastic atomic clocks, nobody's looked, but the day length should be getting longer at an accelerating rate. And so check the record, and it was true. And so, and in a way that's consistent with the other three. And this is my point, is that everybody's trying to prove each other wrong by coming up with some killer way to do it, okay? And so that's the point. The rotation of the Earth is not very fast. It's not slowing very fast. It's not like, you know, you're going to wake up tomorrow and it's going to last for 48 hours and you'll never get out of class or something like that. All right. Finally, there are lines of evidence that come from physics and models. The greenhouse effect is old physics, well over a century old. But climate models invented in Princeton, first ones, are relatively young, about 60 years old now. And climate models, you can run them with and without the anthropogenic forcing from CO2 added to the atmosphere, and you get pink versus blue here. This is from the AR5, and the range of model outputs is shown in the pink. And the black there is the temperature record through that time. And basically, the models can account for the 20th century warming and all kinds of other things, if you include the added greenhouse gases to the atmosphere that not otherwise. And there's a whole lot of other fingerprints. It's not just the fact of the warming, but it's where the warming is. What latitude, what altitude in the atmosphere. Stratosphere cools, the troposphere warms. It's all this stuff that happens that people check and check and check and check and check. And so the models are, in fact, consistent with it. And spontaneously, if you take a model, this is a depiction of the Earth system models at, well, this one's at NCAR, and they're two big national sources. The Geophysical Fluid Dynamics Laboratory across Route 1, and NCAR in Boulder. Boulder's prettier. Our center's better. Anyway, the important point is that these models are nifty in that you turn them on, dark with a rotating Earth, and then flip the sun on. And everything is everywhere. All the plants and animals are all over. Well, there's no animals. All the plants are all over the place. Well, there's animals in the ocean. All the plants and animals are all over the place. There's no seasonality, no weather. And all of that just self-assembles because of the internal dynamics of the system. And it ends up with a climate in a 20th century warming everywhere, approximately within 1% of what's been observed. So that's pretty good now. All right. So multiple lines of evidence, and that's the teaching goals for the lecture. And again, when you're studying for the exam, use those. Should have escaped out, but did not. Okay, Doug. All right, so let's talk a little bit more about impacts. How much can we afford to emit? Anybody know what that is? It's a hurricane. It's a hurricane Hurricane Katrina, which is one of the first that really shook people and really caused people to think that global warming was happening. That's the one that so devastated, especially the poor neighborhoods in New Orleans. Okay, you've seen this before. CO2 is the most important greenhouse gas today, and it's because it's long-lived in the atmosphere. This diagram I haven't shown you. This is the greenhouse warming relative in per unit mass relative to CO2. So a kilogram of methane versus a kilogram of CO2. How much more warming does it cause if it's in the atmosphere? And this is the atmospheric lifetime. And what you can see is that CO2 is down here at the corner. It's at 1 because, of course, 1 kilogram of CO2 warms as much as 1 kilogram of CO2. That's the standard that we're using here to define 1. But its lifetime is out here at 100 to 1,000 years. Methane, as I described last time, is sitting here with a lifetime of just over 10 years. But more than 100 times the per unit kilogram warming of CO2. Nitrous oxide from fertilizer is a potent greenhouse gas like methane, but it's also long-lived in the atmosphere. We're ultimately going to have to deal with that one. That one's a big deal. If we stop using fertilizer, we starve to death. There are too many of us to have unfertilized agriculture now. That's just the way it is. No amount of manure is going to save us, all right? And so this means that to reach zero extra warming forcing, zero extra radiative forcing, we're going to have to offset ongoing N2O emissions with carbon dioxide sinks. There's no other way to do it, okay? Methane we can cut way down, but N2O we really can't. These are refrigerants and other compounds that industry uses. And this guy here, super radiative, but only lasts for days, is black, some kinds of black carbon from soot production. So those are the greenhouse gases. And from the way you should think about it is that everything from here over is short-lived relative to humans. If you wait 3 average lifetimes, 90-some percent, 95% of the stuff is gone, okay? So you'd have to wait 3 roughly 10-year periods to get rid of these guys, or 30 years, which is a while, but it's a generation and it's all gone, right, if you stopped emitting it. Whereas over here, you could stop emitting it and it's still sitting there. And that's shown in the next couple slides. So this shows what happens, just schematically. CO2 is going up, and all of a sudden humanity here in this little realization in 2040 stabilizes emissions. That is, it emits the same amount of CO2 every year. And that's what the blue line shows. This is the annual emission of CO2 under this scenario. And the green says, no, 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 no. We're going to cause emissions to decline over the next 50 years by 80%. All right, now what would happen to the atmospheric concentration that determines radiative forcing? Well, with increasing emissions the way it was in the red scenario, the concentration goes up. With stable emissions, the concentration goes up almost as fast. It's because it's like filling up a bathtub with no drain. Every amount you put in adds to the pool of water in there, right? The pool of CO2 in there. And it's only by decreasing the rate at which the water goes into the bathtub with a stopped drain that the rate at which the bathtub fills up slows down, okay? Now, it's shown to stabilize here, even with 80% less emissions, and that's because, as we'll see in a minute, there are carbon sinks that are still operating on the planet's surface, taking up about 1/3 of the CO2 we emit. So if we were to cut emissions by 80%, we'd actually have slightly declining atmospheric concentrations. If it weren't for those sinks, you have to drop emissions to 0 before the atmospheric concentrations would stay constant. And you've got to wait centuries for the atmospheric concentration to go down because CO2 spends so much time in the atmosphere generally, okay? So it's really important to understand. The opposite is true as methane. If you decrease methane emissions, the concentration of methane will fall catastrophically and quickly on a 10-year time scale because it's short-lived. Okay, so one of the things that's going to be complicated is that most of the images that are available in the literature come from the AR5. And the AR5 uses a bunch of scenarios to talk about the future. And they're concentration scenarios. They're called RCP. R stands for radiative forcing, okay? And so there are different amounts of radiative forcing. These numbers represent watts per square meters of radiative forcing. So the 8.5 is the highest, and that corresponds to a CO2 concentration, which is what's on this axis. It climbs to almost 1,000 parts per million by the end of the century. That's used as business as usual now, and it isn't going to be business as usual. We're already technologically well beyond that. The lowest scenario in the R5 is this RCP 2.6. That one shows atmospheric CO2 reaching a maximum around 2050 and then slowly declining, okay? That scenario is consistent with about 1.7 degrees of warming on average. That's the average number. A little above 1.5, but underneath 2. This blue one here, RCP 4.5, is consistent with, well, here it is. This is temperature relative to how much has been emitted. The blue one here is between 2 and 3 degrees, okay? So that's the AR5. But because we're getting near the end game, the AR6, which, as I said, has just been released, it's 2021, just a couple of months ago, uses emission scenarios, not concentration scenarios. So whereas before we had how many parts per million in the atmosphere there are, and we would have to infer how much emission we're allowed to do to reach those concentrations, here they're actually specifying the emissions of all the big greenhouse gases, okay? And aerosols. And so these numbers, 8.5, correspond to this one, this high emission scenario, corresponds to roughly what you're going to get is the same concentration and radiative forcing in the old 8.5. Not exactly, but sort of. And so this scenario is like the old 2.6. You see it crosses 0 carbon dioxide emissions globally in around 2070 or 2080. And as I said before, that one's going to be, as we'll see in a minute, is 1.7 degrees or so. And they've added this new one, which is consistent with net zero at about 2050 globally and gets you in at about 1.5 degrees, okay? But they also have scenarios for methane. You see everybody's methane is declining. It doesn't go to 0 because a lot of the world depends on rice. And rice is in sort of stagnant water ponds that emit methane. A lot of them do. There's a lot you can do to mitigate it, but not completely. And it doesn't have declining N2O because we need to feed the people of the world, and there are more of them all the time, and they're demanding more food. And who wouldn't? And then the sulfur dioxide, the decrease in the sulfur dioxide actually causes warming. That's an aerosol from burning coal. All right, so these are the now, so I know this is confusing, but it's just the way the literature is right now. So if you're going to look even in the newspaper, all the old stuff is in scenarios of concentrations, all the new stuff is in scenarios of emissions. All right, that's the way it is. So this is the global surface temperature reported and the ranges from all the different modeling exercises reported for these different emission scenarios. And that's summarized in the next table. And what you can see is that because of the long time scale of global warming, we'll look at 2081 to 2100. SPC now, SSP 1 to 1.9 warms just under 1.5 degrees by the end of the century. And remember, it's going to keep warming a bit because of the long time scale and the ocean warming up and all that stuff. So this is a 1.5 degree scenario. I said that one was about 1.7. That's because that's what our model says. The IPCC now says it's about 1.8. And the rest of them look like this. See, this one is close to 3, and this one is close to 4. But on its way, that 8.5 is on its way to, 6, 7, 8 degrees, if you just keep running it. Because of its long life, the relationship between CO2 and the temperature that the globe ultimately reaches depends to a first approximation only on its total cumulative emission, not on its annual emission. There's a fixed carbon budget that you can spend to get to a given temperature, and that's shown on the next slide. So this is the total amount of CO2 emitted since 1850, and this is the temperature, the global surface temperature in 2050, okay, the 2050 surface temperature. And what you can see is this is approximately linear. The more you emit, the higher the temperature, and it goes approximately on a straight line. You see that? So the temperature climbs in 2050 relative to the pre-industrial by 0.5 degree for 2,000 gigatons of CO2 emissions since 1850, all the way up here to between 1.5 and 2 degrees for 3,500 gigatons since 1850. All right? And these are the different emission scenarios. And you can see they're all lying on top of one another because they only depend to a first approximation on cumulative emissions. The cumulative emissions, in turn, allow you to compute a carbon budget and how much burning you have left relative to what we've done before to stay underneath a particular temperature threshold. All right? So this is important. Take a look at this. Historically now, through 2019 at least, we've burned just about 2,400 billion metric tons of CO2. We've emitted that much into the atmosphere, 2,400 billion metric tons. To stay under 1.5 degrees, how many more can we burn after 2019? And the answer is, to be 50% sure of staying underneath 1.5 degrees, we only have 500 left to burn. Now we're burning about 40 a year, so this is just over a decade's worth of burning. And so when you hear in the press that we only have a decade, that's what that means, okay? That's what they're talking about here. Burning at the current rate, we start to exceed the amount in our budget, and we're going to exceed 1.5 degrees if we burn at the current rate for about 12 years right now. Okay, about 10, well, it's 10 years now because this is 2019. If it were 1.7 degrees we were shooting for, we'd have about 850 relative to the historical 2400. But you can see we're near the end. Okay, we're just near the end. All right, so you either accept the big climate change or you basically have to stop. And that's why everybody now talks about getting to net zero. That's what that's all about. It's that you're near the end. All right, enough already. Right, that's the story there. Okay, so it's possible to, and this is why the IPCC went to emission scenarios, right? Because yeah, it's not about the distant future anymore. It's about the next. It's about your watch, right? Your generation's professional lifetime is where we're talking about here. Okay, so where do emissions go now, and where do they come from? So for the decade between 2009 and 2018, which is the last decade for which we have a full synthesis so far, there's one, this is updated every year, but it's always lags behind a bit. The humanity averaged adding just about 35 gigatons of CO2 per year to the atmosphere from fossil fuel consumption and a little bit from cement production. Those are the two sources, but 90-some% fossil fuels. And the rest from tropical deforestation, 14% of it from tropical deforestation. Where did that go? Well, it turns out that of this 5.5 plus 34.7, almost exactly 40 gigatons average, only 18 actually showed up in the atmosphere. You measure the atmosphere, and there's only 18 of those in there, okay? So less than half of it actually got into the atmosphere. Where'd the rest of it go? Well, you can actually track it down. Almost 30% went into the terrestrial biosphere. Plants eat CO2 for a living. You put more CO2 in the atmosphere, plants eat more, and they get fat, all right? And they gain weight. And that CO2 comes out of the atmosphere into the bodies of plants, and that's a transfer, and that's where it's going. And 23% of it is going into the oceans. We'll talk more about that later. So the punchline here is that over half our emissions problem is being handled for free and without our planning by natural negative feedbacks on the Earth, where as we add CO2 to the atmosphere, the biosphere and the oceans take up more. This is just another way to show that. This is the current budget. That's fossil out, land use change, deforestation out, biosphere gaining mass, carbon mass in. That little dot just means that it's an atmosphere, not a flux, not a transfer from one pool to another, and that's gain 19, and so on. So it's just another picture of the same thing. Interestingly, the Paris Agreement, which is going to be renegotiated now, like this week, right? This week and next, says that sources must balance sinks after 2050. Balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of this century is what it actually says. So there'll be a balance, achieve a balance in the second half of the century. You might ask, well, that sounds kind of ambiguous. Does that mean during the second half? Does it mean for the entire second half of the century? And what does the balance between sources and sinks mean? Does it mean that anthropogenic sources have to balance natural sinks? Or does it mean that anthropogenic sinks, like machines that suck CO2 out of the atmosphere, have to balance anthropogenic sources like power plants? And the answer is, we couldn't figure it out one class, and so we actually had the guy who negotiated the treaty come into the class and take questions. He's a really shy person, and so everybody had to be really quiet and careful. And he admitted that they made it ambiguous because they couldn't get agreement if it was precise, okay? So it was TBD, it was to be determined. The way it's been interpreted now with net zero is that anthropogenic sources must balance anthropogenic sinks. That's what we've decided as a species now, and the temperature target is tightening from 2 degrees to 1.5. And there's a reason for that. We'll talk more about that later. In the press, you would think the reason for that is we discovered that global warming is more dangerous. And to some extent, that's true. But what really changed is that the technological alternatives have become far cheaper, all right? So that we can do it right now in a country like the United States at the same cost as not doing it. So then why not, right? Same fraction of GDP we'd have to spend on energy over the next 30 years as we spent over the last 30 years. But at the end of the next 30, we could have 0 emissions from the country. So then what's not to like? Well, if you've got a vested financial interest in the historical technology, you've got a lot to lose, right? If you've got a vested interest in the new technology, you've got a lot to gain. Everybody who's neutral it's all upside, all right? All right. I'm going to skip this. Assuming the world actually achieves net zero in 29 years, the most likely path is U.S. leadership, Chinese leadership, disruptive new energy technology, global economic depression. And, this is just, I don't even know why I put this in. Moving on. All right. These sinks in the ocean and in the atmosphere have existed now since we started measuring atmospheric CO2 every year and measuring emissions every year, which is in the late 1950s is when it began. And then land sink bounces around. Most of that is El Nino, La Nina. El Nino causes big forest fires in Indonesia, and the CO2 comes rushing out of the biosphere and goes into the atmosphere, and then in other years it goes back down again. Some of those are volcanic eruptions that cause cooling, and so it bounces around, but it's been slowly and steadily rising. The ocean sinks slowly and steadily rising. And the amount that's added to the atmosphere every year is slowly but steadily rising. But the fractions that go to these things, the fraction that ends up in the atmosphere has stayed remarkably the same at about 44 or 45%. So why does the terrestrial biosphere and the oceans, why do they take up CO2? And the answer is really pretty simple, okay? The dominant cause of the land sink, as I said, is CO2 fertilization of plants, and particularly forests. There's some contribution from reforestation, but most of it is CO2 fertilization, where plants have more to eat, so they gain mass, and there's more wood piled up on the land surface, and that's what's causing it. Dominant cause in the oceans is more complicated. It's a disequilibrium between pre-industrial waters of the deep ocean and the post-industrial atmosphere, but with the added complexity of a thing called the biological pump. The biological pump is you're not going to be tested on this, so you can just listen. The biological pump, it happens when phytoplankton near the surface of the ocean all of a sudden eat some CO2 that's dissolved in the surface water because they're up near the sunshine. And unlike on land, where only 4% of plant biomass is ever consumed by an herbivore, plants have somehow figured out how to defeat predation on land, but not in the ocean. In the ocean, on average, the poor algal cell that did that is got to wait 3 days and it's dead, eaten by a predator like a little herpacticoid copepod, right? Little one-eyed feeding machine thingy that swims around. And the copepod, in a bizarre, almost accident, has extremely dense poop, which sinks. And so it poops out a lot of the carbon from the algal cell, because it's got incomplete digestion, and that poop sinks down to the bottom of the sea. And so the copepods are constantly pumping the captured CO2 from the surface to the deep ocean. And so the deep ocean is actually supersaturated with CO2 relative to the surface, okay? And that, if we were to stop that, the oceans would outgas for a century and a half, okay? So there's this complication of the copepod poop. But we're gonna forget that for a minute and just think about CO2 dissolving into a liquid the way anything dissolves into anything according to your high school chemistry class, which some of you at least will remember. And there's a thing called Le Chatelier's principle. All right? Bring back flashbacks of bad times or good, depending on what you're interested in. But anyway, Le Chatelier's principle says basically if you have a chemical reaction, if you increase stuff on this side, this direction of the reaction dominates. And if you build up one of these things, this direction of the reaction dominates. And so it reaches a chemical equilibrium. All right? That's Le Chatelier's principle. And so in the, with photosynthesis, if you add CO2 plus H2O, 6 of them each, gives to glucose and oxygen. That's why you have oxygen in the atmosphere, and that's why you have food to eat. That's photosynthesis, invented by evolution several billion years ago. The same sort of thing happens. CO2 in the atmosphere dissolves into the shallow ocean, which gets into the deep ocean by that hydraulic conveyor belt that takes 1,000 years. Remember that story? So the point is, Le Chatelier's principle is operating in both of these cases. We're adding CO2 to this side, and so the right-pointing arrows dominate, and that's the sink. Okay, that's the sink. It's being transferred into the ocean, transferred into land. It's just Le Chatelier's principle. They end. All right. That's all you need to know about that. This complicated slide shows that for the different AR6 scenarios, what the scientific consensus is about what's going to happen to the land and ocean sinks. And the good news is we expect them, even under these most extreme scenarios, to continue to rise as emissions rise. They're going to continue to aid us. The bad news is that the fraction they remove starts to go down. And it's because, for instance, the fridge door effect gets stronger and stronger and stronger, and more CO2 is coming out of the biosphere. And there's a similar mechanism in the oceans. So the sinks are weakened by global warming. The sinks that have been saving us, helping us with more than half the problem, will be weakened if we don't get this under control. And so that is all I'm going to say, because I'm going to get to a new topic now, and I'm going to again continue. I'm going to do the methane stuff next lecture, and keep rolling them ahead. So next year lecture we'll straddle this one and the next one that's on the schedule.